All right, hey everybody. Today we are going to do an old school handwritten notes factoring review. And I have this question mark right here because I know you guys have done factoring before. You actually started factoring in probably maybe even Math 1, but definitely by Math 2 you have been factoring using area models and mostly area models. And I know that that's not typically something that you lock into your memory and understanding the first time you see it. So in order to move forward with our unit, or which would basically be chapter 11 next, we need to stop and really focus in on factoring, because you are going to need to be able to factor a lot in chapter 11. So we're going to stop and focus on that, because if you can't factor, you will not make it through chapter 11. And I'm going to start with the basics here with factoring. So one of the first things we're doing when we are looking at factoring is, first, you will always factor out the greatest common factor if each term shares a factor. So what I would expect you guys to do right now, as you're taking these notes, is to get a piece of paper and pause the video if you need to right now. Pause the video, get out a piece of paper, and write what I am writing. So these are your notes. This is the content that you guys are going to access when you're doing your homework. So write these down. All right, so the greatest common factor, and I'll write that out here for you. So the greatest common factor is whatever each of the terms actually have in common. So let me give you an example here. So example 1, let's say I tell you to factor as much as you can 3x cubed plus 12x plus 6. So if I'm looking at this and I'm being told to factor it, well, it's not a quadratic, so we wouldn't use our the skills we've learned from that. I can't factor out really much of any of these, but each of these terms actually does have the common factor of 3. So 3 is divisible by 3, 12x is divisible by 3, and so is 6. So greatest common factor, you're just taking out the greatest common factor. So I could pull the 3 out of the first term, and I would be left with x cubed. I could take 3 out of 12x, and I would be left with 4x, and I factor 3 out of 6, and you're left with 2. So you should be thinking of it as dividing each of these terms by 3, because we pull that 3 out front. Divide 12x by 3 and you get 4, 6 by 3 is 2. So the greatest common factor is, what is that common term that I could factor out of everything? That's the first thing we're always looking for when factoring expressions. You may have been introduced to this through an area model back in Math 1. By now you should be able to do this simple factoring without an area model, just pulling out that common factor. Now the next type of factoring problem we're going to look at are special cases, and one of the special cases you guys have seen is factoring difference of squares. Factoring difference of squares. So let's write that out. Again, take advantage of the fact that this is a video. If you get behind or you aren't writing as fast as I am, or stumble through a problem and you want to rework it, pause the video. Take advantage of that. That's one of the upsides of this. So I can't talk and write at the same time. Okay. Factoring difference of squares. We covered this together in Math 3 back in the olden days when we did math class together. We did see some of this. So let's look at another example here. Let me show you a difference of squares. I'll show you a couple of them. Actually, let me just show you the formula. So we learned that the formula for a difference of squares, let's say we had, sorry, let me make this a little nicer here. Part A, if I have something that is a squared minus b squared, the formula for difference of squares is whatever's being squared itself. So the a is being squared. In the formula then, that factors to a plus b times a minus b. And this should hopefully at least look familiar. If that's not something you knew or remembered, this is something you're going to want to start to memorize. So let's apply this to a problem. Let's look at a new example. Actually, okay. So let's say let's start with an easy one, x squared minus 16. So why is this a difference of squares? That would be because we have x being squared, and you also want to think about what's being squared to get 16. So I often will rewrite it like this just to emphasize what's being squared. So x is being squared, and 4 is being squared. So then when we go and apply this to this formula, it's really clear what's a and what's b. So this would factor to x plus 4, x minus 4. And if you wrote that in as x minus 4 times x plus 4, that's fine. You can switch around the order here because multiplication is commutative. That means you can reverse the order. Okay, so that's difference of squares. Again, it should feel comfortable. It should feel like a review. All right, the next type of factoring that you guys learned back in Math 2 is factoring quadratics. And that one we definitely relied on area models for. So there's two types of quadratics you guys are going to factor, the simple ones and the not so simple ones. So we'll start with simple ones. Factoring quadratics. TIC. Okay, factoring quadratics. All right, so that would be something in terms of like x squared plus or minus something else. All right, so let's look at another example here. Where did I leave off? Example 2. All right, so let's look at another example. Example 3. Okay, I'm going to show you a few different ones. I'm going to start with something pretty simple. And again, you saw this in Math 2, but we all know that when you just seeing something the first time does not mean you have learned it. So I do want to challenge you guys to take the time to learn this now. It'll be so helpful for you with the content we finished throughout this year and moving on in any math class. Factoring is something you're going to need to be able to do. So way back when you started factoring, we looked at any sum of terms. So we're talking about these three things. If we thought about these as an area, and we used area models to represent them. So we would break down these 2x2 area models for quadratics. And hopefully you'll remember that we would take this first term here, x squared, and put it in the lower left-hand box. And then 12, so we've got the first term going in the bottom left, the last term, 12, going in the top right. Now for this 7x, the 7x, in order to factor, we're going to split that 7x actually between this box and this box, and you kind of have to be clever about how I'm going to break up 7x, because we specifically want the two numbers that will add up to 7, those two numbers also need to multiply to 12. And so you guys were introduced to that concept of these two numbers needing to multiply to 12 and add to 7. You were introduced to that by what we call the diamond game, where you would put the number up top that these two numbers are going to multiply to 12 and add to 7. And then you would think through, okay, what two numbers multiply to 12? 6 and 2, but I can't combine those to add up to 7. 3 and 4, and those do add up to 7. So 3 and 4 are going to be how I split my 7 x's into two smaller groups of x's. So 3x, 4x. And so let's think about this area in terms of adding these up. If I wanted the total area of this box, I would add up each of the smaller areas. So x squared plus 3x plus 4x plus 12. So this is how we're representing our original quadratic here. You can also think of area as length times width. Rather than adding up each of these individual, let's think of it as length times width, and that's the process of factoring. So to get to factor, we're always looking at this bottom left hand first. So if this small square has an area of x squared, that would be a perfect square, and we know that it's the dimensions of that small box have to be x times x. So then I would write that in, x times x. And then this is kind of like that reverse area model game, kind of like factoring polynomials. If I know that this is x, but whatever this is multiplying by over here is 3x, that means the other dimension, piece of this dimension, this would have to be 3 up here. And if this is 3 and I'm multiplying by something to get 12, that means it would be 4 down here. So it should always work. It should always make sense for all 4 of these smaller boxes. So x plus 4, both of those multiplying with both of these x plus 3s should, when you look at each of the individual ones, make sense and add up equaling our original quadratic. So our final factored answer for x squared plus 7x plus 12 is these dimensions. So that would be this dimension, x plus 4, times the other dimension, x plus 3. So length times width. So that's how you were originally introduced to factoring, was visualizing it geometrically as an area, and instead of adding up each of the individual parts, think about it as length times width, and that is what factoring is. Okay, so hopefully that is a clear enough review of how you were introduced to this. I want to try and keep this video short-ish, so I'm just going to keep cruising. If you're confused at this point, stop, rewind, and re-watch. All right, let's look at another example and factor another one. Just kind of get fluid here with doing this. All right, so let's look at x squared plus 7x again. That's just a coincidence, minus 30. Okay, so again, we're going to imagine these different terms being smaller areas in this area model. So I'm going to place my x squared here. I'm going to place my last term. It's not just the 30, it's negative 30. So you take whatever sign is in front of it. So we've got negative 30 here. And then we've got a total of 7 x's that in the factoring process, we'll figure out how to split those between the rest of these two boxes. And in order to do that, again, we're going to revert back to that diamond game. So I need my two numbers that are going to multiply to negative 30. So we put this last value up here, and we want those two numbers to add, see, we're splitting these two numbers to add to 7x, and whatever their coefficients are, they're going to multiply to 30. So we're going to put the 7 down here. All right, so things that multiply to 30, I guess the easiest to think about would be 10 and 3. So can we get, now if they're multiplying to negative 30, you have to hopefully realize if it's a negative, one of those, either the 10 or the 3, have to be negative if they multiply to negative 30. And we want it to add to 7, so hopefully you're piecing together, we can do that with 10 and 3. If I take positive 10 and multiply it by negative 3, those two numbers multiply to negative 30 and add to 7, because 10 plus negative 3 is 7. So that's exactly how we'll split up our 7x's. We'll have 10x here and 7x, nope, negative 3x here. Now if you're wondering, how did I know to put the 10x up here and the negative 3x here? I didn't. It doesn't matter. You get to pick where you're putting those. And then later on you'll see once they're in place, then you'll factor accordingly. So you can put them, you could have put the negative 3x here and the 10x here. It wouldn't have mattered. We'll still get the same result. So let's finish how to factor this. So this first bottom left square has an area of x squared, which means its dimensions are x times x. And then from there, you can kind of build the rest. If this is 10x and I'm multiplying something by x to get it, that means this would have to be 10. So x plus 10 there. And then on the bottom edge, we've got x times what is negative 3x, and that would have to be negative 3. And then we would just double check, does that make sense with the rest of the figures in this box? Because do negative 3 and 10 multiply to negative 30? Yes, they do. So now we've got our factored form of this. So x squared plus 7x minus 30 is the same thing in factored form as x plus 10 times x minus 3. And you guys may have picked up on this by now. Whatever the two numbers are that you got over here actually just end up being the two factors, or the rest of the two factors. I will caution you because that only happens when the coefficient of x squared is 1. So if you'll notice up here, we had x squared. There's no coefficient in front of that. It's just 1. And when I did the diamond game, I got 3 and 4. Well, that's exactly how it factored, x plus 3 times x plus 4. So same with the second one. Did the diamond game, got 10 and negative 3, and those are the two ways that I build my factors. Let's do one more really quick. What I would really love for you to do is after I write this down, I would like it if you paused the video and did it on your own. It is not valuable for you to just mindlessly write down what I am writing. It is valuable for you to practice this and see if you have it figured out. So I would like you to write this one down, pause the video, and try it yourself. Try it yourself, give yourself a couple minutes to figure it out, and then resume the video and check your work. All right, so I want to factor this one. I'm gonna start by drawing my area model again. If you do not rely on area models, you don't have to do it, but you do need to be prepared to show some sort of work if I'm asking for work on a problem like this. So I got my x squared here and my 56 here. So my two numbers that I'm gonna split up the negative 15x between these two boxes. So I'm looking for two numbers that multiply to positive 56 and add to negative 15. So the fact that it's adding to a negative number means one of my numbers has to be negative, right? But it multiplies to a positive number, which actually means both of my numbers have to be negative, because the only way I can get a positive result is if both numbers are negative. So we need to think of two numbers that add to negative 15 and add to 56. If you need some guessing and checking time here, that's fine. Grab a calculator and see if you can figure out what those two numbers are. You probably don't, a lot of people have forgotten their times tables if that's something you memorized earlier on in your education, but the two numbers that add to 15 would be 7 and 8, and 7 and 8 also multiply to 56. But since we want negative 15, those would have to be negative 7 and negative 8, and those multiply to positive 56. So now I'm splitting my negative 15x into negative 7x and negative 8x. So that means the dimensions of my area model would be x times x there, negative 8 here, and negative 7 there. So this factors to x minus 7 times x minus 8. I'm hoping by now you're feeling pretty comfortable with factoring quadratics, these simple quadratics, and they're the simple because their leading coefficient in front of the x squared term is 1. So now we're going to move on to a little bit of more challenging situations where that leading coefficient is not 1, but there's a very straightforward process to help us factor those. So let's figure that out. Okay, so again, you guys have seen these types of problems before. It just maybe has been a while. Let me see where factoring quadratics. I'm going to do a new section here. So section 4 will be factoring quadratics when a is not equal to 1. And when I say a, typically quadratics in their general form are like this: ax squared plus bx plus c. So I'm talking about this number here. In all of the previous examples, that number was 1. If it's not 1, don't worry, we still have a way to do it. So let's review that. It has been a while since some of you have probably done this. So we're going to factor. We're going to start somewhat simple here. And what example am I on? 4. Okay, example 4. So this one, I'm going to start with 2x squared Typically it was 1x squared. We're jumping to 2x squared plus 5x plus 3. So we can no longer rely on the exact method we just did, but it's very similar. The good news is the area model aspect of it, that setup is identical. So these three terms, 2x squared plus 5x plus 3, are still terms that are representing visually some area that we're setting up in an area model. I still put the 2x squared. I'm still putting that down here in my bottom left-hand corner. And I'm still putting the last term, 3, in the top right corner. So now I need to think of these 5 x's. How am I going to split those here and here? But it's going to look a little different because whatever are in these two boxes are impacted by this. One of these is going to have to involve a 2 now. So that's what changes it. The great news is we're still using a diamond game to do this. And our two numbers still need to multiply to 5x. So, I'm sorry, they still need to add to 5x, or 5. So I'm thinking of two numbers that add up to 5. And then instead of placing, like we did in the last problems, we took the 3, this last term, or the c value, and put it right here. Now what you do is you take the a value, 2, and you multiply it by the c value, 3. So always if the exponent or the coefficient of x squared is anything other than 1, then you multiply that by c and put it at the top. So that would be 2 times 3, which is 6. And the two numbers we're looking for in this diamond game now are that they multiply to 6 and add to 5 instead of multiplying to 3 and adding to 5. So what multiplies to 6 and adds to 5? So that's pretty straightforward. We only have a couple of options. 1 and 6 multiply to 6, but they add to 7. 2 and 3 multiply to 6, and they add to 5. So that is exactly what we want here. We've got 2 and 3. So when I go finish my area model, it's 2x and 3x. So those still add up to 5x. That's what we wanted. But now we have to strategically factor. Again, you could have put 3x here. You could have put 2x here. It doesn't matter. The next step will address where you put each of those. So I know that in order for this area, this small area, to have 2x squared, yes, I'm going to have an x squared here and an x squared here, but I also need to put the 2 on one of those sides. Since I have a 2x here, then you just want to think kind of strategically. I could incorporate this 2, if I put it down here on this bottom edge, then that takes care of that 2 as well. So because if I put a 2 right here on this left-hand side, there's not a clean, clean cut number, I guess, to multiply 2 by to get 3. So 2 is not a factor of 3, so I'm actually going to put it down here so it doesn't impact this box, it impacts this box. So hopefully you guys are following my stumbled explanation of that. So I'm going to just leave this side x, and I'm going to put my 2x down here. So yes, 2x times x, that multiplies to 2x squared. And then I can think, okay, 2x times what gives me 2x? Well, that's exactly its own self, so we would just need to multiply that by 1. And then I have x here times what gives me 3x, and that would be 3. And then you just want to double check, does that work with our final box here? 1 times 3 is 3. So that's how we factor something whose leading coefficient is not 1. So that factor then is x plus 1 times 2x plus 3. So hopefully you guys are, again, this is something you guys learned last year, but probably pretty briefly. I don't know how much time you spent with it. So we're going to practice that again. All right, so example B. We're going to do another one. This time we'll do 3x squared minus 20x minus 7. Okay, hopefully you guys are all starting these the same way. area models. You'll definitely need area models for this type where that leading coefficient is anything other than 1. All right, so again, we start by putting 3x squared down here. I put my negative 7 up here. I'm going to be splitting negative 20x's between these two boxes. How will I break down those negative 20x's? To figure that out, we need our diamond. Okay, so I'm still splitting my negative 20x's. So I'm going to put negative 20 down there. But remember, up here in the top, I'm not just putting negative 7, I'm putting 3 times negative 7. So I multiply that by a. So 3 times negative 7 is negative 21. So what we're actually looking for are two numbers that multiply to negative 21 and add to negative 20. So negative 21, there's only two combinations I could get. 3 times 7 multiply to 21. So I think about it without signs. I don't think positive or negative first. I just think whole numbers. 3 times 7 and 21 times 1. 3 times 7 works, but there's no combination of 3 and 7, either positive or negative, that will get me to negative 20 when I add them. So let's think about 21 and 1. Can I get negative 20 by combining 21 and 1? And that answer would be yes. So how do I do that? Well, to multiply to negative 21, one of them has to be negative. And to add to negative 20, that means the 21 would need to be negative. So if I have negative 21 and multiply that by positive 1, that's going to give me a product of negative 21 and a sum of negative 20. So these two numbers here that I just wrote to finish my diamond game are the two numbers that end up in my area model. So that's going to be negative 21x and positive 1x. So just put x there. Now, it doesn't matter where you place each of those. I just happened to put negative 21x there because that was the first number I wrote. Now that I have that there, think about how I'll break down the 3x times x here. So I want to put the 3 on the edge that will be convenient to equaling, getting a product of something that has a factor of 3. So that's going to be this negative 21. So I'm going to put, yes, each of these will need an x to get the x squared. And then the best place to put the 3 will be down here, since 3 times negative 7 is negative 21. So I'll put my 3 down here. And then to multiply 3x by something to get negative 21x, that would have to be negative 7. And then to get x times what is x, that would just be 3x plus 1. So I just want to clarify something. These two numbers, negative 21 and 1, are not the end result of our factors. These are our factors, 3x plus 1 and x minus 7. Same thing with up here. 2 and 3, those were not our end result of factors in the way that they were with these simple quadratics and where the coefficient was 1. In those cases, yeah, that's exactly how you factored it. If the coefficient is anything other than 1, those two numbers only help you complete the area model, which then gives you the factors. So hopefully that's making sense to you guys. So now we have the factored form of this would be x minus 7 times 3x plus 1. All right, so I wanted to keep this under 30 minutes. Let me do one more example really fast just because this type of problem is one that I think people get tripped up on a little bit. So one last problem. Actually, this is a good one to do. So 3x squared, never mind. Just ignore my indecisiveness. 12x squared minus 19x plus 5. Okay, what I would love for you to do right now is pause this video, get through as much of this example as you can without me to check your understanding, and then check your work or hit play when you need some help. Try this on your own. Pause the video, try it on your own, see what you can accomplish, and then resume. All right, so we can start this one by filling in what we can of our area model. So 12x squared is going to be here. And then, oh, come on, 12x squared. And then we'll have a positive 5 up there. And then we need to figure out how to split up our negative 19x's by using an area model. So my negative 19x, or negative 19 there, and then my value that I'm putting up here is going to be the product of 12 and 5. So 12 times 5 would be 60. All right, so I need to break apart 60, factors of 60. So things that multiply to 60, and see if I can get them to add to negative 19. The fact that two numbers are adding to negative 19 means one of them at least has to be negative. But they're multiplying together to get a positive 60. So hopefully you're thinking at this point, okay, my two numbers are going to be negative. But even positive or negative aside, let's just think of factors of 60. We've got 6 times 10. So I'm just going to jot this down up here. 6 times 10. What else? 30 times 2. So can I combine 6 and 10? They multiply to 60. Can I get them to add to 19? No. 30 times 2 is 60. Can they add to 19 or negative 19? No. Any other factors of 60? That would be, what about 60 times or divided by 4? That would be 4 times 15. So those two numbers also multiply to 60. 4 times 15 is 19. That means negative 4 plus negative 15 is negative 19, and they multiply to positive 60. So here we have our two values to break apart negative 19x. We're breaking that into negative 4x and negative 15x. Okay, so now the question comes down to, if I know these are my dimensions here, how do I break down this 12x squared? Well, I know that the x squared pieces of those, that will be 1x here and 1x there. Now there's multiple ways to break apart 12. We could do 12 times 1, we could do 3 times 4, 6 times 2. But we have to look at these other values here. So we've got negative 4 here, which means, and negative 15 here. So negative 4, if you're thinking about how am I going to break down this 12, that gives you the idea that I'm going to need to use 3 and 4 for that. And 3 is a factor of 15. So I'm going to break up this by doing 4x here and 3x there, and then I can do 4x times negative 1 would give me negative 4x, and 3x times what is negative 15x, and that would be negative 5. And then to see if you're on track here, then you can kind of test these last two, negative 1 times negative 5. Those need to multiply to positive 5, which they do. All right, so we've got our two dimensions now, 4x minus 5 times 3x minus 1. Notice we do not get those here in the diamond game. The diamond game helps us fill in our area model, and then the area model helps us determine our dimensions. So our original quadratic factors to 3x minus 1 times 4x minus 5. So hopefully this has been a good review for you on factoring. You need to be able to factor well in order to get through chapter 11, where we're working with rational expressions. So you should be all set to work on your factoring homework now.